Hello, everyone. Welcome to our bi-weekly webcast. It's nice to be with you again. I'm Dave Hoelzer, the host of our little show here. Affectionately, I think of this as Dave's Python Fails, and we'll have an opportunity for some of that this week. But even before we get started, I want to let you know that the next time, so November 12th, we have kind of a special episode for you. We're going to be having on a really good friend of mine, Ismael Valenzuela, who is a super knowledgeable guy. He's worked in SOCs and overseen SOCs and currently works as a principal scientist or principal engineer, I can't remember, for McAfee. Wonderful guy. He's going to be on, and we're going to do a little interview talking about kind of the state of the art of what's happening in the SOC. And when we look at things like AI and ML as they're applied to information security, what's he seeing in the field? What is he seeing at large-scale SOCs and within corporations? Certainly something we can benefit from, maybe get some recommendations or things to even stay away from. So look forward to that one. In the meantime, for the webcast today, you might remember that during the last live stream, we were looking at using a decision tree. And this really rose out of someone who asked a question during one of the live streams. So if you've got some questions, if there's something you'd like to see, anything like that, please do let me know. I try to keep the chat up and keep track of what's going on in there while I'm going. Please do say hi. I'm out here in New York. It's lunchtime for me. I'm actually looking forward to lunch right after we're done here. But the question that someone had asked is, could you solve this problem using a decision tree? And at the time I had said, no, you can't. And we talked a little bit about why that was during the last live stream and actually solve the problem of doing network traffic classification using a decision tree. But I had also promised to talk a little bit about random forests and how they're different, and really, in many ways, how they're tremendously superior. So we're going to do a little bit of that today. And we'll be using some of the same data we've used so far, but we're also going to branch out and use random forests or see how to use a random forest for a very basic computer vision problem. It's actually a really surprising application of random forest. Amazing how well it works. Hey there, nice to have Stephen from Washington, D.C. Stephen is my engineer for this program, so he always says hi to me. Good to have you, Stephen. Thank you so much. And Mustafa, what's the exact issue? Well, the question that someone asked while I was talking, maybe in episode 3 it was, about how to use a deep learning neural network to identify anomalies in protocols, someone had asked, can you do that with a decision tree? And the answer is absolutely not. Because the only thing that a decision tree can do, and the same is true of a random forest, is classify things that it has been trained to find. I can't use it to say, hey, I've got a thing here that I don't know how to put in a box. Because the only thing it knows how to do is put things in boxes it already has. But even though I can't solve that problem, anomaly detection, I can still use these tools really effectively, even with modern problems. And so we're going to be examining that a little bit today. So thanks for asking, Mustafa. Anyway, let's turn back over here and have a look at where I am. I've actually I made a little mistake between last episode and this episode. I deleted the directory. I was cleaning things up and deleted the directory with all the stuff we did with the decision trees. So forgive me. I've put in some code here just to kind of get us sort of to around where we were. What I have here is code that we have seen before that has to do with loading in that packet content or that stream content. Now, Benjamin Finnan. So what is this here? You were going random parse final. Yeah. And I understand why, Benjamin. And it's because I appreciate you tying in that you went with fuzzy logic, because there really is no real fuzziness in a random forest. I mean, there kind of is. The word random's attached to it. We'll explain that a little bit. But it's not great for kind of getting out of the bounds of the training data that you provided. Yeah. So we'll examine a little bit about that. Anyway, the code here, some of this stuff like the data that I'm using actually comes out of the Sec 595 class, which is, 5 days, I almost want to say grueling, but intensive hands-on how to transform your cybersecurity problems into machine learning and AI and data science kinds of things. In fact, if you're interested in that by any chance, there are still openings for the Cdi event that's happening in Washington, D.C. in December. And the current program is set up to run both as a live event in person and a simultaneous live stream. So if you'd like to attend and you don't want to be there in person, that is possible. If you'd like to attend and you actually want to get out of your house, personally, I'm really looking forward to getting out of my house for after 2 years. You can actually come down to DC and join us there for 5 days. Anyway, that's where this data comes from. And the code here, as you can see, is just code to go and find that stuff and load it in. I've got some other little functions in here that I just copied over. I don't think I actually use these. Well, it's figuring out how long things are. Doesn't really matter. This is going to go through and pull in our data and normalize this down to 32 character strings, convert all of that stuff over to bytes. So this is stuff that you've seen in the last episode and actually in maybe the second episode as well, because we've reused this code. Finally, it converts it out to bits using this little shift here. It's just going through and doing the masking to turn it into bits. Anyway, I'm going to run this and just show you what it comes up with, because the interesting stuff isn't here. It's just reporting to me how much stuff there is, how big they are. Some little proof here that if I pass it in characters or a string that's less than 32 bytes, it turns it into 32 bytes. And then finally, taking some strings and converting that from hex, ASCII rendered hex, down to bits. So all of that code works. That's loading up some of that stream data. And the way it's broken out right now is I have data, for instance, in xtest, if it wants to cooperate. It might still be running, though I thought it finished. Let's just see here. Oh, no, it's still loading. So there's a lot of data in there. Let's just wait for that to finish. In fact, while it's thinking, what I should now have is xtest and xtrain, which are two different arrays that I've split apart here. They're actually broken up down here, somewhere around here, or maybe it's raw xtrain, could be that. And then I've got the ytrain and ytest. Those are the labels. Those are the predictions or where it should be, the ground truth. So in each of the rows within the training data, we have the bits that represent what's happening in that stream in the beginning of the stream. So like, the headers, like file headers and stuff. And then in the Y data, we've got the ground truth labels. We use that with the decision tree to make that mapping, for it to work out how to do that. We're going to do a similar thing here with the random forest, but do a little bit of tuning with it. All right, so it appears to have sort of finished here. I've got these different kinds of things that it knows how to, or data that I have. I'm just proving here that the mappings work correctly. I don't know about you. I've kind of learned a lesson, and it comes from, I think, being a programmer for so long and making really simple errors where you take data in, you assume the data looks in a certain way or will behave in a certain way. You then process the data, return, and later you realize your program doesn't work. And when you pull it all apart, it turns out that there's some small little mistake somewhere, and the data just wasn't in the format you thought it was, or you didn't do the transformation the way you thought it was. So a habit that I have, and something I recommend for you, Jupyter really lends itself to this. I'm here doing the transformation where I have taken the data and I'm splitting apart the labels and the data itself, and I'm making sure everything still works and it translates properly. So I have it take a piece of data, something that's an SSH request, transform it to whatever the mapping is. So these are just the indices for the different categories. Here it's 16, and then telling me what that maps back to, SSH request. So just proving that all functions. With that all done, so I actually didn't name it X test. I think it's X raw train and X raw test. No, that's wrong too. Hold on, let's see here. Raw X test, excuse me. I did tell you that this would be Dave's Python fail, so I am living up to my promise. So there we go. So I've got the raw training data. There it is. And I've also got the Y train. So that has the indices, and what you have there is each row. So if I pull up a row, it's telling me that whatever is in X test, so raw X test sub 0, those bits map over to whatever that particular mapping is. Now, I can use random forest to solve this. Before I do, I want to show you a little bit of a thing that I worked out before you came. It's a demonstration I'll frequently do because it's just very powerful in looking at random forest and explaining how it functions. And then we're going to come back to this data we've just pulled apart, and we're going to plug that into the random forest and see how well it does. So I'm going to make use of a toy data set here that comes from sklearn, but it's also available in most of the different machine learning libraries. Most things that offer data sets will provide this. TensorFlow does, PyTorch does, everything's got it. This is better known as the MNIST dataset. Now, the MNIST dataset is a whole bunch of 8 pixel by 8 pixel images of handwritten numerals, and the goal is to create some kind of computer vision or classification system that can take the handwritten digits and convert them to a computer understood number. So if someone draws a 0, it can look at that and say, that's a 0. It can distinguish one from the other. So this is a classification problem. It's a toy data set because even though that's a real problem, at this point we consider it to be pretty much a solved problem in computer vision. So the data is just used for testing and demonstrating and learning a little bit. Maybe if you develop a new approach toward machine learning, you'd use this. I'm here going to use the load digits from sklearn to pull that on in. And I actually feel like I want to load that a little differently. Well, let's just see what I get here. So I'm loading in the digits. So this is the MNIST data. That's the handwritten digits. And after that, I'm also pulling in matplotlib. These are images. So I can render these things out as pictures. So what I'm going to ask it to do is to render for me one of these digits, or actually a number of them, with matplotlib. I'm asking it to create a series of plots. In this case, 10 images by 10 images, so a grid of images here, so that I can see some of these images, see how they've loaded. And then I'm using the imshow to show me the actual MNIST data as it has been loaded. When I do this, you can see, and I've actually intentionally let them be kind of small, because it turns out that if I render one of these really big, you're going to look at it and say, I have no idea what that is, because it's just so spread out. But by rendering it like this, you can make out, oh, okay, this one over here, this looks like it's a 3, and I think that's a 2, and that's a 6. So you can make out most of them. There are a number of handwritten digits in here that are very difficult to make out. And in fact, when we look at our solution, we're going to find that the computer solution is probably at least as good as a human would be, because some of them are so badly written. In fact, my handwriting is so bad, I wonder if they've got samples of my handwriting in here just because they're so awful. In any event, we've loaded those things in. What I'm going to do now is similarly split that stuff apart. I'm going to create some test data and some training data. Now, this is not the same as a neural network, because when we use a neural network, we run the data through the neural network training process multiple times in an epoch, and we run them through in batches of data. And what's happening during that training process is that it's updating all of the parameters within that neural network in order to be able to learn. That's not what a random forest does. It works in a very different way. And there really isn't a need to go through the data many times. So we're going to break the data up into train and test, not because I need to run through multiple times, but instead because I want to build the tree and then see how well the tree works. So we're actually keeping that test data set aside for a very similar reason, for validation, to know that it actually functions. I'm pulling this apart for both the train data and the train labels. And then here, I'm loading in the random forest classifier. Now, I am just curious, if you don't mind, if you actually tuned in to the last live stream where we were talking about decision trees, if you wouldn't mind, just give me a little shout out. I'm kind of curious how many have followed along and maybe been with us through our journey here. And if you're new to the stream, you know what? Let me know that too. That's totally fine. I'm interested in just anybody who's here. So if you've been here before, just put something in the chat. Let me know that. If this is your first time through, drop that in the chat too. Of course, remember, I'm happy to have questions. And if you're finding the content interesting or useful, then please like or subscribe if you're on YouTube. Or if you're watching this on LinkedIn, go ahead and follow our LinkedIn channel. In any event, in our last one, you might recall that I imported the tree, the decision tree, out of a different branch of sklearn. Decision trees are not found within the tree classifiers. Instead, they're found in the ensemble set of learners. The reason why they're here and why it's under ensemble has to do with the definition of that word. An ensemble is a collection of things. You might think about an orchestra. Well, you could also call that an ensemble. It's a group of instruments. So here, random forest classifiers, it's not one tree, it's actually a group of trees. That's even implied in the name because it's not called a random tree classifier, it's a random forest. So it's a whole bunch of trees. So we're going to load that in. I've got a little function here that's just to measure overall accuracy. And then here, I'm going to start with a really simple random forest. In fact, I'm just going to go ahead and run that. And I do not expect this to work well. Okay, hang on. I've got a little error here. Xtrain is not defined. Well, it looks like I defined it. Maybe I forgot to run this cell. Okay, let's give that a shot. There we are. It is already done. It has trained the classifier, has an overall accuracy of 72%. I know that was so blazing fast in how it did its training. But it's only 72% accurate, and that doesn't seem very good. Part of why that is, though, is because how I have gone about training or building this random forest. When you build a forest, one of the things that you get to define are how many trees you would like to have in your forest. So we've got a couple of, hey, Stephen Lord, nice to see you. I feel like I haven't seen you over in Slack in quite a while. Nice to have you back. And again, hello again, Mustafa. For the number of estimators, this is the number of trees that we're going to have. We've also got another newcomer. Hi there, Benjamin. I feel like I've seen your name before, but maybe not. Maybe it's just a name that's been like that. Or maybe you talked to me earlier today. I find as I get older, my goodness, my memory is so bad. So maybe it was just that I saw you earlier today. In any event, the number of trees to use. And as I even say that, there's kind of an interesting thing here, because an idea you might have or an intuition you might have is that using a random forest means there's more than one tree, but how can having more than one tree be useful? For example, let me change this from one tree to 10 trees, and we're at 93% accuracy. That's pretty interesting. How about 100 trees, 93%? And we may not get much better than that. The reason is that there's similarity in different protocols. For instance, how much difference is there between an HTTPS request versus an HTTPS response? So it may not be able to get there. We actually can see here an example of some of the superiority of using a neural network. Because when you begin to deal with very complex data with complex relationships in it, a deep learning neural network can often find those relationships that are not as easily found using something like a decision tree or a random forest. For example, when we trained a network on this data, the training definitely took much longer, but you might remember if you were tuned in for that. Oh, wait, I'm sorry. I'm actually thinking of two different problems now, aren't I? Because I'm not yet classifying the network data, but when we were classifying the network data, we got to 100%. We don't yet know how it does or how the random forest does with that. I forgot we're currently working with the computer vision data. But 93%, that seems pretty good. Can it get better? And the answer on this problem is really no. And it comes back to this issue of some of the numbers that are in here are, take this one over here. Now, I actually can't tell. Can you guys let me know? Can you actually see my mouse? Because what I'm doing right now is just sharing a tab out of my browser. I usually share like a region of my window, so it's a little different for me. So if you cannot see my mouse, if you could let me know that would be pretty important. But I'm looking here. If you count from the bottom, 1, 2, 3, 4, the fourth row up, and I'm looking at the number that is on the far right. And if my mouse is visible, it's where my mouse is. Oh, great. Thank you very much, Stephen. So this number right here, what number is that? What would you classify that as? Is that a 9? Is it a 4? I don't know. That one's kind of a rough one. You got another one over here. So since you can see my mouse, this one down over here. What's that one? Is that a 1? What do you think? Could that be a 4? Maybe it's a really bad 7. We've got another one over here. This one down at the bottom. That looks more like a G, but I'm going to assume it's a 9, or the one next to it. I mean, I guess that could be a 1, but it could be a 4. My point is that there's no wonder it doesn't get to 100% on this problem, because not even a human could do this at 100%. Most of them are unreadable. But the curious thing that happened when I changed the number of trees. Because when we started out with one tree, we got 75% this time. And if I rerun that, that number may change, 69%. I'll explain why momentarily. But when I move that up to, say, 10 trees, whoop, we shoot right up, 92%. With one tree, we're never going to get higher than the mid-70s. But with multiple trees, we can easily get over 90%. How is that happening? Well, when a decision tree is built. The way a decision tree is built is it takes a problem. What it's trying to use is really something that comes from the field of information theory. If I tell you something you already know, that doesn't count as information. What we're trying to do in conveying information is to reduce entropy. You can view entropy in a simple way as stuff you don't know. So if I'm telling you stuff you already know, there's no reduction in entropy. But if I'm telling you something new, even if it's just one new fact, I have reduced your entropy. Well, when you're passing your data into your decision tree, what it's trying to do is figure out how can it best break that data up? What feature can it look at? Which pixel can it look at? That if it breaks the data on that pixel, it will generate the greatest information gain. It will divide the data, in a sense, most evenly. So maybe it's the pixel right in the middle. So is that on or off? We split them right in half. And then there's another pixel, and we split again and split again and split again. So that's how a decision tree is built. Now we're back to that intuition, though. How would a random forest be better? Because if a decision tree is built in that way, then really decision trees are deterministic. But even as we can see here, when I run this with one tree, I get, wow, 79%. I get different results every time. So what's happening? Well, that brings us to the random portion of this. The random portion is not that we randomly generate the tree, but instead, which features are being used to build the tree. That's random. And which samples within the training data set are being used to build this tree. That's random. And what it's using is a thing called bagging or bootstrap aggregating. I'm not going to define it any better than that. We don't need to go down into those details. If you really want to know, you want to know the mechanics and be able to really use these things effectively. I mean, that's what that Sec 595 class is about. In any event, so it does this randomness in figuring out which features to use and which elements of the data to use. But still, it doesn't do amazing. Why does it do better when we use a larger number? Well, what's happening is every one of those trees is using a different set of features, in this case pixels, to decide what to do with the data, and is also using a different selection of the data itself. That results in the trees all being different. How does the classification work then? Well, every tree gets one vote. All of the trees get to vote on what numeral they expect this to be or that they predict it is. And whichever numeral, so we have 10 categories here, whichever one gets the greatest number of votes, that's what it must be. All right. Oh, that's interesting. Thank you very much, Stephen. So the mouse is only visible when I'm moving. That's super good to know. Now, if I crank this up to 1,000 trees, you'll see it actually takes longer to train. But we also see one of the benefits of using the ensemble methods. This really didn't take terribly long because since it's an ensemble method, many different trees, and since those trees are all distinct from one another, it can actually build many trees simultaneously. So even though I've asked it for 1,000 trees, it's still able to train very quickly. In fact, you might notice that there's two sets of output here. The output here at the top, that's the training, that's building the tree. This part down here, that's me asking you to run predictions because it's still going to parallelize that task over all of your different threads. That's one of the great abilities or great values of using a random forest because I can spread the load out over many different processes and make full use of whatever resources I have on the machine. Now that brings me back to, can we classify the network data? So I'm going to take a little bit of stuff here. I'm just going to grab these pieces. Well, actually, I guess I'm grabbing that whole thing. And I'm going to move on up. Where am I? So I think Echo. Okay, so here's where raw X test was. Let me just add some cells to this here. I'm going to just paste that stuff in there. It's not quite ready to use. Let me look at raw X test again. Okay, that is definitely data, and raw X train. That looks good too. There's sort of a curious thing here. You'll notice that my arrays here, they actually don't have numbers in them. I mean, look closely. Sure, you see ones and zeros, but look closely. You see those numbers are in quotes? So it's actually passing in characters. It turns out that with a decision tree, it pretty much doesn't matter because it's not using the bit values to try to find meaning. It's just trying to break the data into pieces. Whereas if I were using this with a neural network, that's going to be a bit of a problem, and I would have to make these into numeric values. All right, so let me then see if we can pass that data in here. Let's do a little tinkering. So down here, the maximum number of samples, I don't even think I'm using that code. Let's just get that out of there. We'll keep the accuracy function. That seems useful. Number of estimators, again, let's start with just one. And forest.fit, let's fit on raw X train. And I have to look up what the name of the labels are because I don't remember. So let's just take a peek up here. Let's see, we called it Y train and Y test. And let's look at some of that. So Y train. All right, so that is outputs a different category for each. Yeah, and it is individual labels. Yes, it is. So that looks good. Here, Okay, it was making me suspicious. It was very convenient that it was a 0 and a 2. Okay, so it is definitely the training data. So let's map this to Y train. Ooh, I think I used, okay. Good thing I was suspicious because I think we used Y train down here as well. Yeah, we sure did. So that's really going to mess up our decision tree. So let me just reload that data. So I'm sorry, we're going to have to be just a little patient there while that reloads. It'll take a little while to do it. And then we'll just check and see if the value of that is something different than 8. In the meanwhile, let's see what I've got here. The rest Y train, so that seems fine. And then we're going to do some predictions using raw X test and compare Y test to predictions. That all looks right to me. I'm sure something will break, so we'll just get that started here. I'm doing it with one tree to start with, and we'll see how it goes. Now, while that's thinking, I want to ask you folks again. I have told you that our November 12th live stream is already set. We're going to do that really good interview with Ismail, hear a little bit about SOC operations and the influx of data science and machine learning into that space. But I'm really looking for suggestions from you folks on what might be good to hear about. So any of you are welcome. Any suggestion or question. It does not have to be machine learning or AI related. It could be pretty much anything to do with cybersecurity. And I'm very happy to do a live stream on that. So if you've got something you've always wanted to see or some Python code you want to see me fail writing, please put that in the chat there. Or if you'd like to, reach out to me afterward. Ping me over LinkedIn maybe. Send me a message there with what your idea is if you're not watching live, but you still want to participate. In fact, you're always welcome to reach me over there. Feel free to connect with me and send me messages that way if you're looking for more questions or answers for questions. All right, so this is no longer showing an 8, so that's good. I'm using the right training data. And well, did I run this cell? I think I must have. Let me try one more time. I'm just so suspicious that it worked the first time. It does look like it's working. That's a good sign. No errors coming up. You'll notice it is taking longer to train. Now, part of why it takes longer to train is that it is a lot more data. There's also a lot more features present. So the training takes longer. All right, looks good. And I got a 94.75. Wow, that is outstanding. I wonder if we can do better. Now, right now, what I'm asking it to do as it builds this, and we haven't looked at these yet, but I'm telling it that for each tree, it may only use a maximum of 8 features or 8 pieces, 8, in our case, 8 bits out of the stream to decide what it is. It's actually pretty surprising. It gets 94% using just 8 bits in the data to decide what it is. However, I'm also letting it build the tree down to a depth of 20. So that is pretty deep. Let me reduce that. Let me change it to a depth of 5 and say that after 5, you have to tell us what it is. Let's retrain that. And I suspect our accuracy might decline a bit. Just experiment a little bit here. And what I'm doing right now is I'm testing it with 1. I'm expecting to get a low value, and then I'm going to start increasing the number of trees. And we're going to see if we can improve it using a very small depth, because the better we can get with a smaller depth, the better off we are, because we're getting a lot better balance across our trees. So we're still looking pretty good here. We're still at 90% using a max depth of 5. I am really surprised it's doing so well. Let's up our estimators. Let's go ahead and give it 20 trees. See how well it does. Do we want to let it use more features? Sure. Let's let it use 16 features. Off it goes. And let's see how well it does with that. Especially because we're using the max samples of 1,000. So that's the maximum number of samples it can use in any training iteration. That means that it's quite likely, given this data, that every tree is being trained on different data. That's pretty impressive. It's doing so well so quickly. One of the things that says, though, is actually an answer to the name of this live stream. This live stream today was, are random forests still valuable? And the answer is yes, they absolutely are. In our case here, let's see, we're up to 97.54%. That really is excellent. Now, this noisy stuff here is not particularly pleasant, but we can make that go away. I've only it's only doing that because I've turned on verbose so that you could see the parallel training occurring. But I think you can see then that this can very, very easily be used to really do any kind of classification problem you have. What's the limit then? Well, let me recap. The original question was, can I use this for anomaly detection? Because that's really what we had been talking about during the other live stream. The answer was no, and here we can see why. Because right now I'm giving it data and it's coming up with an answer. But let's do a little experiment here. If I have a look at one of the samples that's in raw X test, so there's what all of the data looks like. Let's take one of those. So that thing is of shape 128. It's got 128 bits in it. So here's what I'm going to do. I'm going to say not TCP data equals np.1s 128. And let's just look at that. TCP data. There you go. It's got an array of ones in it. They're not even ASCII characters now. They're actually integers. And let's try to run a prediction on that. Now, in order to do it, so we could just come up here and grab our predictions code and my accuracy here. Well, I can't really use accuracy because that isn't anything. There's nothing for that to be. Let's paste that in here. So when I try to use this, now this is going to fail, and I expect it to fail. It's always better when I expect it to fail. That failed. I want to show you how it's failing, because if you try to do this kind of stuff, the errors you get can kind of mess with you sometimes. It's saying, I expected a two-dimensional array, but I got a one-dimensional array instead. Now, this actually turns out to be a pretty useful bit of help. This is coming out of sklearn. The stuff that TensorFlow gives you is much less helpful than this. It's giving us, here's how you fix it. But why is that a problem at all? Well, the reason is that what it's expecting to get as input, it is not expecting to get something that is that shape. What it is expecting to get is a whole bunch of rows that are that shape. But I'm not passing that. I'm passing a single row of data. Now, there's a couple of ways you can approach that. One way you could do it would be to take this and put it inside of square brackets, and that will make it work. You can see here, I'm now getting a prediction. I don't really like to do that, though, because to me, for someone looking at this later, okay, I can see that you're putting that in a list, but I don't know why you're putting it in a list. It's non-obvious. Is that just how you have to call it? And the answer is no. The problem is the shape of the data. What I need to do is to change this from being one row of 128, or just really a single dimensional array. What I need to do is make it a two-dimensional array that has one row of 128 field or pieces in it. How do I do that? Well, there is this handy reshape function that's available in NumPy. And of course, I have 128 right now. So if I did something like this, 64, 64, 2, and hit enter, you can see it will very happily turn it into 64 rows of 2 columns. If I ask it to show me the shape of that, it is as expected, 64, 2, or 32, 4. No problem. What if I want to change it to something like, let's make it 4, but I'm not sure what the other dimension would be, or I don't want to work out the math? Well, it turns out that you can give it a -1, and it will work out what the other dimension should be. Now, of course, it has to be something that it can actually solve. So if I use 3, that's not going to work because I can't do that with a 3, but I can do it with an 8 and most powers of 2. Well, we have a sort of similar kind of problem. I have something that's shape 128. What I'd really like to do is make it that shape. That shape is one row or one set, one thing that has 128 columns in it. This is now a two-dimensional array, and my data is still the right shape, 128 bits. So personally, rather than doing this, which is shorter, I know it's shorter, but I really prefer to reshape like that. Because if I do that, it is much clearer what I am doing in there. In fact, I'm going to hit Alt-Enter here so I can see the predictions. And here's the thing. It comes back and tells me that is protocol 11. Now we can translate that. Somewhere up here, I've got a translator for this. Let's see where that is. Mapped is Y test I. Okay, so it's unique labels sub. Okay, so I just need to access what's in unique labels. Unique labels. Oh, wait, I'm in the wrong place here. Hold on. We're down here. Unique labels. Even further. Even further. There we are. Unique labels. So this is the dictionary, or is it? It's either a list or a dictionary. I don't remember what it is at this point. Probably it is a list, and tells me that that is QTLS. Now, wait, I might have lost you there because, we covered a lot of ground. I just did a prediction against an array that looks like that, and it tells me that's QTLS. All I did was create an array of ones. Let's make it an array of zeros. Let's do that again now. It's all zeros. Do a prediction, unique label, and it says, oops, it says, oh yeah, that's DNS. That does not look anything like DNS. What's happening is it has to call it something. It only has bins for things it knows. There is no way in a decision tree or random forest to create a bin that says, I don't know what that is. Now we can get away with that in a neural network. I'm not going to get into how in this live stream, we're already almost 45 minutes in, but I can do that by examining what the output probabilities are. In fact, rather than viewing the output layer simply as what class it is, I could view it as a probability distribution. And based on the density of that probability distribution, I can tell if it doesn't really know what this is. And there's an even more powerful way to do that using an autoencoder. And we've actually already covered that ground. That's also something we spend a great deal of time with in the SEC 595 class. So if you want to learn how to do that, to do anomaly detection based on what's going on in logs, what's happening in your network data, what's happening within other statistics and data you're gathering out of your environment, that is definitely a class to investigate. On the other hand, if you've been looking at this and you find it kind of interesting, but the whole packet thing is really an unknown for you, well, you might want to do what Stephen did, Stephen Lord, who took the 503 class. And the reason I know his name is because Stephen spent a good amount of time for at least several months. I feel like it might be several years, not just taking that class and being successful, but then helping other people, because we have a community that surrounds that class in a Slack channel. And people continue to participate and ask questions and help each other out. So if you really want to know how these networks work, how to defend a network well, and do threat hunting on a network today, take a look at that SEC 503 class. At this point, though, we are at the end of this month's live stream, or this week's live stream, and the last live stream for this month. If you enjoy this content, please do like or subscribe, or if you're on YouTube or on LinkedIn, please follow and get notifications for when we have future live streams. We try to be very consistent with this one once every 2 weeks, and our next one is already scheduled. Remember, Ismail Valenzuela will be here. If you have other thoughts or ideas or questions following this live stream, feel free to reach out to me over LinkedIn or otherwise put things in the chat in our next live stream. Thank you so much for tuning in this time. I look forward to seeing you again on November 12th.